Hello and welcome, Max Mathias here, continuing with the Math for Econ series. Today we're going to be talking about univariate calculus. My disclaimer before this starts is we are in no way covering everything to do with univariate calculus. I like to think of this as really an applied kind of short class of everything you need to basically deal with any single variable functions that you will be encountering during your time in an economics major. So why do you need calc for econ? This is a question I get all the time. Math underpins almost everything we talk about in economics, right? I generally think we do a pretty good job of hiding it in principles levels classes when we're drawing demand, when we're drawing supply, when we're talking about, firm profit maximization, all of these things. But fundamentally, economics it's math. Right? It's applied math, and I like to think it's common sense math, but it is math all the same. What I really like about it is it's math that has these kind of common sense real world applications, unlike doing math for just math's sake. And so another way of kind of thinking about this is math is how economists communicate with each other. Right? We generally will draw, if I'm trying to explain econ to my mom, I'll be drawing graphs or kind of just talking about a general principle. But if I am communicating with another economist, we're going to be using math, to more or less kind of explain things to each other. That is what economics papers are all about. The important thing here is it's to retain the common sense thread through the math, not lose it, right? Again, we're not doing math just to do math. We're doing it because ultimately it is helping with our model or giving us insights about, economic reasoning of agents, things like that throughout this. We're not just doing math for fun, although my students would not believe me when I say that. And just a practical example, whenever we say marginal economics, right? So if you've ever taken a principles of economics class, you'll hear things like marginal benefit, marginal cost, marginal revenue, anything like that. Really, when we say marginal in econ, we mean the derivative, right? All objects we discuss basically from intermediate, micro and beyond, demand, supply, revenue, profit, anything like that, they are functions. And we're going to use the derivative ultimately to inform kind of our decision making as we go forward. So what is a derivative? It's the instantaneous rate of change of a function at any given point. Rate of change is just the slope, right? So like for something like a straight line, it's quite easy to find the slope. You don't need to do much work. But if you have something that's a curve, well, all of a sudden it's much harder to find the slope at any given point. The derivative gives us the power to do that, and in a pretty convenient way. Now, the definition of the derivative, right, is it's basically we're looking at how this function is changing, adding this just very, very small incremental thing, h, right? So it's f of x plus h. So if I add just a little bit more to this function and subtract what I had before and then divide it by that amount, ultimately that is giving me the slope. As h gets smaller and smaller and smaller, obviously we're getting a more kind of accurate thing of what the slope is at any given point. It's important to know, though, that we can't evaluate this as is, right? You can't divide by 0 as h goes to 0. Economics, we don't really need to use this definition of the derivative. Again, I'm just basically telling you what we are finding here. There are some very common derivatives, which I'll talk about on the next slide, but it's important to kind of understand what we're doing here, right? And then a quick notation note throughout this video. I will use the df dx notation when taking a derivative, right? Df just because that is the function f, but it can be anything, right? If we're talking about a utility function, right, u, it would be du, and then whatever's in the denominator there is what you are taking the derivative with respect to. It'll be x here, but in your economics classes, it will be thing like q, quantity, L, labor, K, capital, right? Doesn't really matter, but it's always basically the function is in the top, and then what you are taking the derivative of is in the denominator. You also see people write it as, f prime of x. I'm fine with that. It doesn't translate as well when we kind of do multivariate calculus and partial derivatives, but again, I'm not going to fight you on this. If you like writing f prime of x, go for it. So derivative formulas to know, there's a few. Power rule. All the power rule says is that if you have some function x to some power n, its derivative is you basically are bringing the numerator down in front n, x, and then you subtract 1 in the numerator. So n times x to the power n minus 1. You're going to use this all the time. This is probably the most common derivative that you will take. It applies for negative exponents. The one that is also there that a lot of students kind of struggle with is just like a linear function, right? X, the n there is 1. Right? So when you're doing that, you're bringing the 1 down, and then x to any power 0 is just 1, right? So whatever is there stays there. That's one that I see students miss all the time. The power rule is applicable for everything, basically except not even accept the natural log, right? The natural log leads us to a weird thing, right? Where natural log of x, its derivative is 1 over x. Honestly, I can't think of a thing where the power rule doesn't apply. So very useful. You'll use the natural log one, particularly when you're doing utility functions like Cobb-Douglas, but also if you're doing something like econometrics or whatever, log is a very useful function that we use all the time. The last one is just a constant, right? So if your function f of x is just some constant c, that is, it doesn't depend on x in any way, shape, or form, then the derivative is 0, right? And the way to basically think about that is this number is not changing. So because it doesn't depend on x in any capacity. So if I change x, well, the value of the function doesn't change, so it's 0, right? Constants not multiplied by x fall off when taking a derivative. The way I like to think about this is if you have some function where there's a plus sign or something like that, think of the plus sign as your chance to kind of relax, right? If you have, two terms added together, take the derivative of the term before the addition, take the derivative of the term after the addition, the plus sign is going to stay. So if you have something like x plus c, it's just going to fall off, right? But if that constant is multiplied by x, well then either the power rule or the natural log is going to apply. But constants on their own, basically they fall off, they disappear whenever we take the derivative because they are constant. They don't depend on x, they don't change. The one thing I will talk about here is the chain rule. So it's used when you have one function of x kind of inside another function of x. So a way to kind of think about this is something like the log of x cubed, right? We can basically think of this function x cubed is inside this larger function, the log, right? So how do we deal with that in derivatives? So we write this as basically f composed of g of x, right? So our function f basically has another function g inside of it. So when we're taking the derivative here, the reason why this is called a chain rule is you're going to take the derivative of the outside function f times the derivative of the inside function g. So in math notation, when we're taking this overall derivative, you're going to take the derivative of f with respect to x, but you're still evaluating it, so to speak, at g, and then you're going to take the derivative of that inside function g. So for our example function above, log of x cubed, if I wanted to take the derivative, so df dx, so if I basically think of the log as kind of the outside, I know it's 1 over whatever is inside, so we write that 1 over x cubed, and then that x cubed inside, we have to take the derivative of that as well, which using the power rule is 3x squared. After simplifying that, watch my exponent algebra video for things like that, you would get 3 over x as your ultimate derivative. Another way of viewing the chain rule that a lot of people think is easier is U substitution. So what is U substitution? Basically, you think of that inner function g as a new function u equals g of x. So this then simplifies to two functions. You're going to have f of u, and then u is g of x. So you're going to take the derivative of that f function with respect to u, and then the u function with respect to x. And so mathematically, this actually works out, right? df dx is basically just the derivative of f with respect to u, so df du, and then times the derivative of u with respect to x, du dx, and you'll notice the du's basically cancel, and that's how we get that. So at the end, you'll plug back in for x wherever you see u, right? Whatever that g of x is, you plug it back in, and that'll work. So if we were to use the example from the prior slide, right, log of x cubed, how would I go about thinking about this? Well, that inner function x cubed is going to be my u, so u is x cubed, and then my new function f of u is just the log of u. And then I can basically do this piecemeal, right? So the derivative then of u with respect to x is 3x squared, that's the power rule, and then the derivative of f with respect to u is just 1 over u, that is that log rule that we talked about. Now plug back in for x wherever you see that u, and you multiply them together. So doing that math, we're going to have 1 over x cubed times 3x squared, 3 over x, you get the exact same answer. If u substitution is easier for you, absolutely do it. Again, the biggest mistake I kind of see with people when trying to do derivatives is they try and do too much at once, right? Instead of breaking it apart into kind of easier chunks to do, they try and do everything at once, and ultimately they make an algebra mistake or they make a derivative mistake. So take your time, I promise it will be better that way for you. So let's test your knowledge. So what I recommend is that you take a few minutes, right? Pause this video, try these problems. I have 4 functions for you to just take the derivative of. I will give you the answer in just a second, but highly recommend pausing it, testing your knowledge, and we'll go through it. So for our first function there, the answer you should have gotten is 6x, right? And the way we do that is just very simple power rule, right? You move that power down, the squared, and so then 2 times 3 is 6, x, and then 2 minus 1 is just 1, so 6x. That second function, you should just get 12, right? Again, we are using the power rule there for x. It's implicitly to the 1. So 12 times 1 is just 12, and then the x goes away. And then that plus 100, if you kind of use that advice, 100 is just a constant. Doesn't depend on x. It goes away when we do the derivative, so you're just left with 12. For the third one, this one's a little bit tricky, right? So this one is where you would do the chain rule, right? Or use u substitution. So you can think of our inner function there as being u equals 2x plus 5, which its derivative is simply just 2. And then 1 over u would be our other derivative. So you're going to have 2 over 2x plus 5. There's no simplification we can do there. So a little bit messy, but it's one that, again, if you just kind of think through it, use your chain rule, use u substitution, whatever works for you, you'll get the answer. And then lastly, for the 5x cubed plus log of 2x, you're going to get 15x squared. That is a very simple just power rule application. And then that plus, basically take a breather, work through it, right? Think of it as kind of doing a new derivative for the log of 2x. That will just simplify to 1 over x. So either if you've watched my exponent algebra video, you know you can separate those out to log 2 plus log x, in which case the log of 2 just falls away. But if you wanted to use like the chain rule or u substitution, you would wind up getting the derivative of that inner u function is 2, and then the derivative of the thing itself would be 1 over 2x. So 2 over 2x, the 2's cancel, and you're just left with 1 over x. So the entire derivative is 15x squared plus 1 over x. So with that, I hope that you got some use out of this, and I hope that you were able to get the answers for these. But if you got anything out of this video, please consider liking and or subscribing. Thank you so much for watching. Let me know in the comments if there's anything that I need to go over or clarify, or if you want to see an additional video, new topic, anything like that, let me know. But I'll see you next time.